Okay, so this is where we start looking at fluid dynamics properly, and fluids are quite interesting because they can move information through a fluid by the mechanisms of diffusion and convection. So we kind of know about diffusion, which is molecular transport of, say, heat through a steel bar, and this happens in a fluid, and convection, where the velocity of the fluid actually moves information. So if you imagine you've got hot fluid and you put it in one end of a pipe, convection of the fluid is moving that energy from one end of the pipe to the other. And fluid mechanics is quite interesting because the relative strength of these convective and diffusive fluxes control the type of physics that we see. And we know about this already because we have diffusion and convection of momentum. And when the convective flux of momentum is much, much larger than the diffusive flux of momentum, the fluid is unstable and it goes turbulent. And this is represented by a large Reynolds number. You've seen the experiment that you've done at the start of the year looking at the instability of a dye in a pipe. And so we use non-dimensional numbers to characterize this balance and to characterize the flow stability. And this is really important for us to understand things as engineers. So if we want to create heat transfer from a solid to a liquid, how we stir the fluid defines how much heat transfer there is. Okay, so this is really key information to understanding what's going on in fluid mechanics for you to be able to use it as a design tool. Okay, so this is a two-part lecture. It's two lectures in one. So the first thing we're going to do today is we're going to think about what is convection and diffusion, define it, and come up with a simple convection diffusion equation. Okay, and then in the next lecture what we're going to do is we're going to understand what that equation gives us when we put some boundary conditions and some assumptions on it. And we're going to non-dimensionalize that equation, and we're going to generate some non-dimensional numbers from that non-dimensional process, that process of taking out the dimensions from the equation. And this is a much, much better way of working out what these non-dimensional numbers are and what they mean. So this is very useful compared to something like the Buckingham pi theorem, where you generated the non-dimensional numbers and worked out what the relevant non-dimensional numbers are for a particular problem. But the issue with the Buckingham pi theorem is that you had to know what these numbers, these non-dimensional groups, were to recognize them. So you actually derive these non-dimensional numbers from the equations themselves in this process. And this allows you to understand what's going on. And the final reason this is important is that it allows me to give you an explanation of why we separate the fluid mechanics teaching we do into inviscid flow and viscous flow, which happens right at the end of the module. Okay, so this is all background kind of stuff to fluid mechanics, and once we've done these two lectures we then start going through and doing proper calculations with them. Okay, so let's think about convection and diffusion. So if we have a steel bar and one end is hot and one end is cold, and we know that heat's going to flow from one end to the other end. So if it's a steel bar and you put one end in the fire and you hold the other end with your hand gets hot because all the heat is travelling up the bar. And if you did it with a piece of stick, wooden stick, and you put one end in the fire and you held the other hand, your hand wouldn't get hot because heat flows at different rates in different materials. And the material constant that controls all this is the thing called the thermal conductivity. So the diffusion depends on two things. Diffusion depends on the temperature difference between the if you like, the source and the sink, and it also depends on a diffusion coefficient, and for energy it's the thermal conductivity. Okay, and convection is effectively the action of velocity to transport something with it. Okay, so in the example of poo sticks, it's the stick and the river. The river's velocity is transporting the stick down the river, and if you win the game, your stick gets transported faster by convection than your friends. Okay, so and in reality, in real life, in fluids, we have convection and diffusion going on together, and when diffusion and convection dominates is really something that we're interested in. So a classic example is a candle flame, and we've got two variables here that are being transported. So the first one is fuel, or wax if you like. So wax heats up and melts, and so there's lots of wax at one end of the candle, wick, and effectively at the other end of the candle wick there's no wax because it's all been burnt off. So there's a diffusion coefficient of wax through the wick, and there's a gradient of wax concentration. So there's lots of wax at the bottom and there's no wax at the top. So diffusion processes pull this wax up through the wick. Okay, so wax transport is purely a diffusional problem in a candle. And then we start thinking about energy. So energy is created from the combustion. So, and the hottest part of the candle is the bit at the bottom, the blue bit. And so we get the combustion because the oxygen goes in and the wax evaporates and burns and creates some energy. And then we have, so once we get some heat, the density reduces. And then because the density reduces, there's a buoyant flow, so there's velocity in the candle upward. So convection is carrying energy vertically away from the candle and heating the room, hopefully. And but energy is also diffusing downwards, more or less. And so, for instance, the energy from the combustion is diffusing through the air to the wax, and it heats the wax up and goes back. Okay, so in terms of energy, effectively, convection is taking the energy up, and diffusion is taking the energy down. Okay, so we've got diffusion of energy and convection of energy that's acting in two different directions. So they've designed candles to get this balance right over centuries without sort of thinking about fluid mechanics, but understanding this kind of process is kind of quite integral to designing fluid machinery. And convection diffusion of energy is going to be the subject of this and the next lecture, and we're going to take this kind of analogy of energy flow in a candle. Okay, so let's just try and work out how we define convective and diffusive flow of stuff. So by stuff, what we're interested in is our three master variables: mass, momentum, and energy. And typically we talk about an intensive, extensive variable which depends on the amount of stuff there is. So we've got a certain mass, a certain momentum, and a certain amount of energy. And in the previous lectures I've talked about an intensive property which doesn't depend on the amount of stuff that you've got there. So the intensive variable for mass is density, so that's mass per unit volume. The intensive variable for momentum is velocity, so effectively velocity is momentum per unit mass. And enthalpy in terms of energy per unit mass. Okay, these two things can be related by this equation here, which we've come across before. So we use intensive variables to define these fluxes, and this is where they're useful, and this is why we like them. So classic example, let's say we've got two large plates at two different Z positions, and we've got a one-dimensional flow in the X direction, and we're interested in how much energy is flowing through this section. So if we take a control volume like this, and we say, well, let's invent an area in the middle, and we want to know how much energy is flowing through there per unit time. So effectively, this is the power. This is the thermal power flowing through this surface. Okay, so we're interested in enthalpy flow, so this is energy flow per unit second, and we can work this out really easily because we've got the mass flow, which is kilograms per second, and the specific enthalpy, and the kilograms cancel, and it gives us joules per second. So this is quite easy to work out the enthalpy flow. We just take the mass flow and multiply that by the specific enthalpy, and we know the mass flow m dot, m is rho, a, and u, and then we've got the enthalpy here. So this, and then the area we can see is dy in this direction and dz in this direction. So this term here, this is my enthalpy flow. Okay, so we've done it for enthalpy, but you can do it for anything. If you want to do it for mass, you just you don't bother about this. If you want to do it for momentum, you set EH to U, and if you want to do it for energy, you use EH. Okay, so this is the general case of defining a convective flow of our three key variables. So when we start thinking about diffusion, we have to think about diffusion of energy and diffusion of momentum, and these are a little bit different. So let's think about diffusion of energy. So the simplest way to think about this is there's no convection. So this thing here might be, let's say it's a steel bar, and this is my hot surface, and this is my cold surface, and I'm interested how much energy is flowing through my little test surface here due to diffusion. Okay, so we need a law that defines my thermal flux. So a flux is a flow per unit area. Okay, and it's defined by two things. It's defined by the diffusion coefficient. So for energy, that's thermal conductivity, which is this K, and it's defined by the temperature gradient at the point we're interested in. So this d by dx bar x means this is the gradient at x, so at this point, for instance. Okay, and if we know those two things at x, then we can work out the thermal flux. So this law is called Fourier's law. So if we want to work out the energy flow, we have to multiply this thing by the cross-sectional area of the thing that we're interested in. So that's dy by dz. So we end up with something that looks like this. Okay, and we have a boundary condition that we have to apply. So this technically should have been in the previous lecture, but we didn't know what this equation was, so I've put it here. And we have to make an assumption about what's going on at the wall. And there are two ways that you can apply your boundary condition. The first thing you can do is you can say, well, I'm going to assume the temperature of my wall is constant. Okay, so this TW here is constant, and what that means is that the flux through the wall is not fixed. The flux through the wall depends effectively on what T1 is. So if T1 is smaller than TW, the flux is going to go from the wall into the domain, like this. But if T1 is bigger than T-wall, then the flux will change direction, and the energy will flow from the fluid through the wall and away. Okay, so that's one assumption that we can make. A more common assumption is that we define a constant heat flux. So you might get this from, you can think of an example is if you get a saucepan of water and you put it on your stove and you light the gas. So effectively you're pushing a certain amount of heat into your saucepan, and the temperature of your fluid is changing over time. Okay, so that means the temperature of your wall is effectively changing over time, and what's happening is the gradient at the wall is always the same, and because the gradient of the wall is always the same, you've got constant flux. Okay, and a special case of this is where it's a completely insulated wall and there's zero heat flux through the wall. So a classic example is a thermos flask or a double glazed window, hopefully, and in this case Q is set to 0, so effectively your wall temperature and your internal temperature are fixed and constant. Okay, so that's transport of enthalpy, and so effectively what's happening here is the heat flow is always in the direction of the gradient. Okay, so this gradient is defining your direction of heat flow. Okay, so diffusion is always a spreading process, and you're always, if you like, flowing down the hill. So you're flowing from the hot temperature to the cold temperature, and that's the direction of heat flow. So when we start looking at diffusion of momentum, it starts getting a little bit more complicated. So remember, momentum is a vector. So in this particular, if we have a case where we've got a large plate here, and we've got a large plate here, and our plate at time t0 up here is doing nothing, then at time t1 our plate starts moving at a certain velocity, and then at a much later time you have this fully developed velocity profile. Okay, so how do we get from this case to this case? Well, effectively what's happening is momentum at the no-slip boundary, so the fluid next to the wall, due to the no-slip boundary, is moving with the wall velocity, and effectively momentum, so that's momentum in this direction, diffuses in a direction normal to the wall. So momentum is here and it diffuses downstream until it gets to a steady state velocity profile across like this. Okay, so, and this diffusion coefficient is defined by the viscosity. So if you have fluids such as air and water and golden syrup, say, they will diffuse momentum much more efficiently, and this velocity profile will appear much more quickly in a more viscous liquid. Okay, so the relationship between, if you like, the deformation of the fluid and the stress that is applied is the governing diffusion equation for momentum, and it's this equation down here. Okay, and just to sort of point out that this du by dy, this is actually the rate at which you're straining the fluid or deforming it, or the rate of shear strain. So the rate of shear strain is the strain per unit time, and it's shear strain, so it's the deformation in the x direction. So if we start off with a lump of fluid like this, a little bit later time it's like a rhomboid. So the deformation in the x direction is this little term here, and the length in y is just delta y. Divide that by time and you end up with du dy. So when you see the velocity gradient, it's not just the velocity gradient, it's the rate at which you're straining the liquid. Okay, and experiments have shown for most fluids that the stress that you apply, so this stress is the force that you're applying to the top of the wall divided by the area of the wall. That stress that you apply at the wall is defined by the viscosity and the velocity gradient. Okay, So this is our sort of master equation. This is the same as the Fourier's law. So we still have a diffusion coefficient and we still have a velocity gradient, but you have to remember you've got your momentum in the x direction and it's diffusing in the y direction. Okay, so it's a little bit different. Okay, so the viscosity is known as the dynamic viscosity, and sometimes you might see it as the kinematic viscosity. And these symbols are almost always the same in textbooks, and the kinematic viscosity is just the dynamic viscosity divided by density. And this relationship is known as a linear stress-strain relationship, and a fluid that has this relationship is called a Newtonian fluid, and it's a linear relation, and all of the fluids that we're going to be looking at in this module all have this Newtonian assumption. Okay, so now we're going to start thinking about how do we write conservation of energy in a convection diffusion problem. Okay, so we're going to have a very simple problem, and we're going to write a conservation equation for a control volume in this problem. Okay, so we're going to say we have a long channel in the x direction, and these two plates above and below are large, and the velocity is constant. There's no viscosity here. So we're going to assume there's a uniform velocity across here, and it's one-dimensional and it's steady, and the density doesn't change. Okay, so we're going to sort of make up a section in the middle. So we're going to say at x equals 0, I have a low temperature here, and at x equals 1, I've got a hot temperature here, and the velocity is going this direction from left to right. So what that means is convection is blowing cold fluid into this region between x equals 0 to x equals 1 that we're interested in. And on the other side, we've got hot fluid here and it's cold fluid over there. So diffusion is going to be trying to push hot fluid into the domain that we're interested in, and the convection and the diffusion directions are opposed. So this is a little bit like my candle example right at the start of this lecture. Okay, and what we're interested in is what's the temperature profile in this gap, and how does it depend on the velocity and the liquid physical properties like the thermal conductivity, because the temperature difference is fixed. Okay, so this is what we're interested in. This is what we're going to work on for the rest of this lecture and also the first half of next lecture. Okay, so we've got a control volume, and we're going to assume that we know about everything at the center of the control volume. So that's kind of this big X location. So we know what the velocity is there, we know what the temperature is here, we know what the temperature gradient is here. Okay, and we're going to do a control volume analysis of energy conservation over this kind of test volume. And so what we need to do is we need to work out how much stuff is going into the control volume, and that's going to have to balance how much stuff is going out. And that's because it's steady state, so there's no accumulation of stuff in a control volume. So dA by dt is 0, and we haven't got any chemical reactions or anything else going on, so we're not going to create any energy inside the control volume. So it's steady state, so that means whatever energy flows into the control volume must flow out. And when I say flow, it can flow out by convection and it can flow out by diffusion. And because it's one-dimensional, we've only got two faces that we're interested in. We're interested in the upstream face, which is this one here, and we're interested in the downstream face, which is this one here. So we've got a diffusive and a convective flux on this face, and we've got a convective and diffusive flux on this face, and the sum of all these four fluxes have got to end up equaling 0. Okay, and that's what we're going to do. So how are we going to estimate what the value of stuff is on the upstream and the downstream faces, we're going to use a Taylor series. We're going to assume our control volume is really small, so we're going to use a first order Taylor series. So if we want to work out what the downstream, if we want to work out what the temperature is on this face, if we know what the things are in the middle, we can use a Taylor series like this. And if we want to use the face here, want to work out the face here, then that's this particular one here. So we're going to use these repeatedly. Okay, so let's work out the convective flux balance on this control volume. So what we're going to do here to start with, we're going to assume that there's no diffusion. So there's just convection. So the velocity is going from left to right. So energy is flowing in and energy is flowing out. And the amount of energy flowing in must equal the amount of energy flowing out. So we've got to work out the convective flux on this face minus convective flux on this face. And the difference of those two must be equal to 0. So we can work out what the enthalpy flow is at the control volume center, because we know everything there, and we know that that's the mass flow times the specific enthalpy, and we end up being this thing here. And then we say, well, okay, we've got this expression. So which of these variables changes as we go from x to x minus dx over 2, or x to x plus dx over 2? And if we think about it, the density is not going to change, the velocity is not going to change, Cp is not going to change, the area is not going to change. So it's only the temperature that changes. So how does the temperature change? Well, we don't know, but we're going to say we can do this using a Taylor series. So we can work out what we estimate the temperature to be on these two upstream and downstream faces, which are these two variables. So we can then, if we want to work out the fluxes or the enthalpy flow on these two faces, we take this expression here and we put it into there. And then for the other face, we take this expression here and we put it into there. And then we've got our two energy flows. And we take these two things away. So we say what goes out minus what comes in must be equal to 0. So the convective flux on the upstream face minus the convective flux on the downstream face must be equal to 0. So if we've got this expression with this thing in there, and then we've got another one of these minus with this one, we take those two things away. That term and that term are going to cancel, and effectively these things will add together and make dt by dx times dx. So these two things will add together. So we end up with an expression that looks like this. And if we want to make it a little bit more simple, we can get rid of the volume. So we end up with an equation like that. So if we have no diffusion and it's pure convection of energy, then this is this must hold. Okay, this must be true. Okay, so now let's try and do the same sort of thing with diffusion. So at the moment, what we're assuming is that there's no convection. Okay, so we've got diffusion through if you like, a non-moving fluid. And if we're at the central point, we know everything, so we can work out the flux at the center. That would be this. And if we wanted to work out the energy flow during diffusion, the diffusion energy flow at x would be this d at x, and that will be the flux at x multiplied by the cross-sectional area. So that's that distance plus this distance. Okay. Same sort of thing as before. We want to work out the fluxes at these two things, the upstream and the downstream faces, and we can extrapolate our flux Q up and down the control volume away from x, and we can come up with these two expressions to work out what this flux is. And then we do the same thing that we did before, and we say, well, there must be, if there's no convection, the amount of diffusional energy flowing into the control volume must be the same as the diffusion energy flowing out, because there's no accumulation. So the upstream diffusional flux minus the downstream diffusional flux must be equal to 0. So we take effectively this thing multiplied by the cross-sectional area minus this thing multiplied by the cross-sectional area, and that term will cancel, and you end up with d by dx of qx multiplied by dx. So effectively this thing. Okay, so this thing, and then we substitute in our expression for the diffusional flux, and we end up this, and this thing must be equal to 0. So we should have a minus equals 0 on this side here. Okay, so if there's no convection, this thing must be equal to 0 if it's a diffusion dominated problem. Okay, so we've got that. So now we have to think, well, we've got we said we had diffusion and convection in the same problem here. So we can just say, well, the amount of convection, the net amount of convection plus the net amount of diffusion must be equal to 0 in this problem. So effectively we can just add our two equations together and set them to 0. Okay, so we end up with this expression here. So this is our convective balance, and this is our diffusive balance, and the sum of these two things, or these two equations added together, must be equal to 0. And then we can simplify this a little bit, so we can divide by the volume of the control volume, so we can get rid of this bit, and we rearrange it slightly by having a coefficient here which contains all our fluid physical properties. So this is my thermal conductivity, this is my density, and this is my specific heat of the liquid. Okay, so we've got our velocity and a first order derivative of temperature, and then we've got some material constants here and the second order derivative of temperature. So this is our convection diffusion equation, and we're going to see what happens when we change U and this constant here relative to each other. We get different temperature profiles. We want to understand what's going on. Okay, so we know how to define convective and diffusive fluxes. We know what the diffusion law is for heat and the diffusion law for momentum, and we've come across the balance of convection and diffusion. And this link here is you should never believe what you read in the newspapers, especially the Telegraph, because this is just nonsense. Okay, have some go through and revise all of this, because we're going to be using this equation next week, and we're not going to be doing any more revision questions until we've done with this section. Okay, thank you very much.